Well, it's great to be here with you guys this afternoon, and it sounds like you have gotten a lot of value out of this. And I attended some of the sessions, and I really enjoyed them. Really interesting stuff. Now, you might have looked at this description and started thinking, what does that even really mean, the principle behind principles, right? It's kind of got something to do with this. Do you know what this is? This is what we used to call an architecture astronaut. Have you heard about this at all? It's kind of good because it's then kind of disappeared, or maybe like in this part of the world it wasn't ever a thing. But there was a time when basically there were people in the software industry that would try to generalize things that should not be generalized. And they basically try to make things fit together in interesting ways. And it could be problematic because sometimes they would never deliver. And nobody likes that. So the thing is that this is an experiment in having a little bit of fun and seeing if we can generalize from some of the things that we can to be design principles. And frankly, we have a whole bunch of them, right? Some of these might look familiar to you, right? There's kind of like, command and query separation principle, dependency inversion, cohesion and coupling are things there. Liskov design principle also. Liskov substitution principle. So there's so many of these things. They've developed over, a long time. And so it's an interesting thing to go and sort of ask, when we have these design principles, are they new all the time? Are we reinventing them? What's really going on with this? So let's go and take a little, scan through history a bit, So I look at the modern era of software development as starting in like the 1970s. There was a lot of stuff that happened before then, but just really not as interesting. And what happened as we started going through the decades is we basically had dominant paradigms, dominant ways of going and designing things and working with code and working with systems that became very popular. And it's just like that typical thing of like a hype cycle, where it's like, yay, it's like everybody gets into this and it's going to solve all of your design problems, all of your coding problems, everything along those lines. So I think the key first one was really structured programming. And this was basically formulated by some people that went to a conference, I believe in Oslo, from all around the world, and basically representing that it was so hard to build complex big systems. Something needed to be done. And back then, they didn't even really have high-level programming languages, or they just had gotten them. And you had this thing of trying to figure out, what do you make with these things that doesn't turn into a tangled ball and mess? So they basically came up with some principles, and cohesion and coupling were among them. And then a couple of other things like don't use gotos to jump outside a function, which is something that used to be possible back then. It was kind of crazy. But the next piece of this also is really like the era of object orientation, and this was huge. The number of developers that basically entered the industry at that time was amazing because people looked at object orientation as like the thing that was going to save the complexity problem, or basically sort of solve the complexity problem that we have in software. And it didn't quite work out that way. We ended up growing and creating terribly complex things. And actually there was a lot of failure too. A lot of people basically, they sort of like looked at it and said, I think I know what's going on with this. And they started marching into it, and then they discovered like way later that what they were doing wasn't going to work. And it was a real problem, right? 90s, mainly consumed by client-server software, and then the advent of the web, those different things. Microservices and DevOps in the 2010s, and now we have serverless and a lot of platform engineering. But these are just kind of like these waves of interest, things that people think are going to be the way that you go and do something in order to solve some of the problems that you currently have. If we go and look in at a micro scale, it gets even more interesting. Somebody ever heard of Conway's Law at all? Okay, it's this notion that when you basically go and when you basically design a system, the structure of the software starts to mirror the teams that produce it. So if you basically have a big system and you have two teams working on it, chances are there'll be two main components. That's just a thing that happens naturally in systems. And structured programming, I mentioned that a little bit earlier. That was a big thing that came around 1968. And it was all about, when you think about it, basically making it easier to understand the code that we were writing so we could change it easily. The next big thing was information hiding. And this guy, David Parnas, he did not invent that in 1972, but he sort of first wrote up the idea. And the idea behind this is that essentially if you have some piece of software, and back then it was all just sets of functions, they should hide a design decision. You should be able to go through the interface of a thing and then basically not have to know what's inside of it, right? And believe it or not, that was something that a lot of people didn't really think of as a big deal back then, and he had to go and sort of champion this particular idea to go and get things moving in a sense. So information hiding, cohesion and coupling. Separation of concerns is another thing too. It's like you have some things are spread all across the system. Why don't we make all the database access go through this particular service, for instance, or this particular set of classes? And when you separate your concerns, you know where to go when you basically have found a problem or when you need to make a change. So that had to be kind of championed also. The robustness principle, this one right here, is really about going in, organizing systems so that when they receive input, they can receive input that's sometimes bad in a way and still keep processing. And so they take this input, but they have to make sure they produce really correct, regular output. And if you basically make systems like that, then you can link them together. And that's something that basically has kind of tied itself into network protocols and stuff along those lines. There's controversy about it, but that's a big design principle. Okay, 1980s. You ever heard of this one before? The Hollywood principle? What's the difference between a library and a framework? Usually with a library, you're basically making calls into it to have it do things for you. With a framework, it's kind of like it gives you an area that you plug something in, and then it calls you in order to go and do some task that you specify. And the idea back then, since that wasn't terribly popular, was just to go and sort of like start to orient software that way. So essentially, the life cycle of things started to become managed in a sense for us, and we just have to figure out the pieces that we plug in and kind of work with them. Command query separation principle, you've heard of this one at all? Okay, this is an interesting one. It basically says if you have a function or like in a system, it should basically either go ahead and modify the state inside of an area, or it should basically return a value back to you, but it should not do both of those things. Anyone know why? It's a mixture of concerns. We get back to separation of concerns again. If in this thing you're going and working on producing the thing you're going to return, and you're also modifying state in various areas, that can be very problematic in terms of reasoning about the system and how it works. Single responsibility principle. I'm sure people have heard about this one, right? This is like a core of design practice, and the idea behind this is essentially that when you have a thing, it can be like a class, or it can be a method or a function. It should have one core key responsibility, and essentially if you start to add more responsibilities into it, it gets convoluted and hard to go and work with, and that's just a problem, and so we things start to grow. Open-close principle. This is an interesting one. In the modern formulation, what it's basically saying is that when you're going to modify parts of your system, it's really nice when you don't have to modify stuff that's there. You just kind of plug in new code. Right? If you have to change a lot of things to get your feature in, then it's kind of like the design could probably be better. And it took a while for people to see this, but this open-closed principle is kind of tied to single responsibility principle. If you break things down by single responsibilities, it's like, here's the responsibility of this thing. Chances are it does it and it does it well. I won't have to change this all that much. Right? So you basically get areas of closure, areas where you don't have to make changes, and then some points they're kind of open to extension. So if you target single responsibility, you get open-closed naturally in a sense. And this is the thing that happens over and over again with principles. Somebody thinks of something, and they say that this is a great guideline for the industry. I'm going to put it out there and tell people about it. And then somebody will later go and discover it's like, oh, it's kind of the same as this one, right? But I don't think that's really bad. It's kind of like the more ways you can get at good design knowledge when you're doing your work, I think the better things happen to be. 1990s, it's kind of like Spring and all these other containers for inversion of control. We basically started going and doing a lot of that, and I think it's interesting because it took a lot of time to undo it, also in many cases. Convention over configuration, that was a big thing. Like I think Ruby, basically Rails and Ruby was one of the first things to go and actually say, look, we've got a strong opinion about how this works. You follow this direction, and you'll be able to make something that works well for you too. Not this thing of going and sort of like saying, okay, well, here's all these options, and you can get to select each one of these things. No, this is a very focused thing, right? Okay, dependency inversion principle, probably not worth getting into, but it's really more like if you have some module or class or something, it's more like you should not depend upon things concretely, but just depend on a protocol that gets you to communicate with the other piece. This one, don't repeat yourself, is one that's basically just been very popularized as well, right? You ever hear don't repeat yourself when you're writing code? It's like you end up having duplication in the code base, and then it's hard to go and figure out where to make the change. Well, maybe you think you know where to make the change, and you do make the change, but you discover later you need to make it in the other place also, because it's fundamentally the same code. So we try to go and remove duplication as much as possible. And when these two guys, Andy Hunt and Dave Thomas, first described this, they did an interesting thing. What they were basically doing is saying that this doesn't apply just to software. If you have documentation someplace, you don't want to go and have duplicate documentation that has to be updated and might go and fall out of sync, that kind of thing. And so a lot of these principles are really very general in terms of how they apply. In fact, as well. Actually apply to social systems as well. Tell, don't ask is another one by those two, Andy Hunt and Dave Thomas. And the idea behind this is that if you have a system, you should really basically not set it up so people are asking you questions all the time. Instead, you do your work and you pass it on to the next thing, right? What happens when you basically have an API where people are getting and getting and getting all the time? All of that computation tends to be focused in you. And that's almost like an attractor that people want stuff that you have. But if you basically have a protocol where you do some work and you pass it on to something else, your chances of keeping this thing small are often much better. So it's a nice design principle. Okay, 2000s, kind of going forward a little bit too. You've heard of the solid design principles? Yeah, a lot of you have, right? And Robert Martin basically formulated those in the 2000s, and they're really kind of centered on object orientation, but some of them really are very applicable in other areas as well. Have you heard about KISS? You know what that is? Keep it simple, stupid. Okay, does this actually apply outside of software too? Yeah, it definitely does, right? Having that mindset that you want to keep things as simple as possible is really, really useful. Principle of least astonishment. You should not, I think you call this like what, WTH per second, right? And like just how often you look at something and you're stunned by it, and you really think nothing like that could happen in your system. And so it's like there should not be continuous surprise when you actually go ahead and work with something. One of the things places where this can happen is like you can be working and then discover, like here's a message you've never seen before, and you don't know what it is, right? Or basically here's an exception being thrown you didn't even know it existed. You don't know under what conditions that would occur. And it disrupts your idea of how things worked, and you have to go and start to rebuild a model of how things work to get your work done. Rule of 3, this is something which applies to general systems design. It's like if you basically need to copy something just to get something working, if you do it 3 times, by all means, make sure you remove the duplication. Otherwise, it just gets out of control. This is the same as that dry principle I mentioned a little bit earlier, right? Like, don't repeat yourself. But it goes and points to an answer. When you do repeat yourself, basically take action, at like maybe the 3rd instance of duplication in order to go and refactor things and basically remove the duplication. Anybody ever hear of the principle of least privilege? Okay, this basically says users of a system should only have the access that they need, never higher access levels. And it's a security principle, right? There's package design principles, which is about organizing, large software projects. Law of Demeter. I'm going to kind of skip over that because it's not terribly germane. What I'm doing is I'm going through a lot of these different ones just to get you a flavor of the kinds of things that people have seen as powerful guidelines in the past, right? If we jump into the 2010s, it's kind of like, there's some things that basically were kind of like pushed, API first design, continuous everything, which is kind of like, we can just write code and put it into production like this, right? Which is kind of like an enveloping term to like, continuous integration, continuous delivery, and everything else that falls into that area. And there's immutable infrastructure, so you have Docker and all these things, so you get to deploy things and know that they will never change, as a client of them. Fail fast, you've heard of this? When something goes wrong, make sure you fail fast and you don't try to go and continue the computation, because if you do, it makes it harder to debug and see what's going on with this. Does this apply in other systems other than software? Fail fast. In organizations, it can be really powerful. If you discover that you can't do the work that you're working on, best thing you can do is basically just be transparent about this and tell people that this is not working, right? And we need to basically talk about how to do this. Or if something goes wrong, the same kind of thing. Just basically make sure that you raise the flag, because if you don't, things can go on for quite a while with a lot of a lot of stuff that's not known in the context of the team because nobody's surfacing that information. And then we get to the 2010s, 2020s. And there's zero trust architecture, so basically sort of checking everything from a security perspective. Defense in depth, which is kind of related. There's one I love, which is single source of truth. There should be, if you have data in the system, you should be able to find it in just one place. If it's scattered around the system, then you're kind of in trouble. And that can even tie into responsibilities in the system as well. Testable architecture, okay? If you've seen, basically Neil Ford has been basically talking about this using the terminology of fitness functions. And the idea behind this is you can actually write tests to basically test the capabilities that your architecture has particular capabilities and qualities, and just have that kind of thing running in the background. So it isn't a thing of kind of like working with it and kind of hoping that it still has these particular KPIs or something like that. Okay, so there's that, and then there's this other one which I think is really interesting, Hiram's Law. Has anybody ever heard of that one? It's a little bit different than most of the other ones, and it's really more of an observation. What this guy said is that if you present a public API to something, right, any behavior that goes through that API is something you're stuck with, generally, as you have more users. Because they'll think that your accidents are really intentional behavior. A great example is you give a list of names back to somebody, and then basically you've sorted it. And every time that you basically return it, it's sorted. But the thing is that basically you never made a promise that they were going to be sorted, and someday you do something else and they're not sorted anymore. And what do people do? They start saying, what do? You're breaking my system. It's kind of like these things used to be sorted and they're not now. So you just have to recognize that when you put things in production with many users, they depend upon the behavior that you have, even the things that you don't even intend to reveal to them. And that's kind of a wild thing. So we have all these principles. They kind of like ride on top of these different waves of different ways of doing things, the different paradigms that are there. And I hope you can see that some of these things are kind of similar to each other across the ages. And it's not like the idea of cohesion and coupling went away. It's more like it's kind of surfacing in various different principles and practices. So one of the things I was kind of wondering about is this really all just because of technology? As the technology changes, we basically go ahead and sort of discover problems, and maybe we weren't people that had experience with the last level of technology, and we couldn't really transplant those ideas easily. And maybe we thought we invented them ourselves, which is kind of interesting, right? So it's like, I observed this, and this is great advice, so you pass it along to everybody so they can go and sort of benefit from the advice that you have. It turns out that this is like a very natural process. There's a guy named Cesar Hidalgo, and he worked at MIT, or he was at MIT for a while, wrote this wonderful book called Why Information Grows. And he basically started thinking about how knowledge grows in systems. And he was talking about the thing of like you're in a city and it becomes very dense with people, and then people see opportunity, they want to move to that city. And the growth of knowledge about how to do things is very rapid because you run into people accidentally at the coffee shop or something and start to grow knowledge and things like this. But the other thing he talked about a little bit was this, kind of like how knowledge grows in systems through the eyes of like music genres, right? I mean, there's very few people that listen to swing music from the 1920s now, or ragtime music. And that kind of slowly dissipated over time. There's some people now that listen to things from the 80s and from the 90s, and maybe in 20 years that won't be happening as much. But you always have like that trailing, couple of decades that you kind of look back into. If you're a kid, maybe it's because you have like, recommendations or even old records from somebody like in your family or something like that. So it's not like these things really last forever. Some things do, particularly in the classical world and the jazz world. It's like people start to recognize that this was a very important performer, artist, or composer, and they just sort of like keep, and their knowledge of this person alive, and it works. So this is the kind of thing that happens in software development, and we go ahead and we just kind of reinvent things a bit, and it's, it's okay, right? So the thing is, it's kind of interesting because it feels to me like a little test bed in a way, because I'm always thinking about what's common and what's different when I'm looking at things. And so this is an experiment in going and trying to find out what's really common among all these principles, or really as many as I can fit in a generalization. Before doing this, though, I have to explain a little stuff that's kind of like a little bit out of software, and it's going to seem like it doesn't link, but it will. Okay, so essentially there's this thing, let me go and jump, I have one slide there. There's something called Galileo's scaling law. And what this is essentially an observation made by Galileo way back in, I guess, the 1600s. He kind of recognized that there's this interesting thing that as things scale, they have to change structure. If you've ever seen one of those, crazy monster movies where they have a giant ant attacking the city, you're like, oh wow, that's scary. But if you realize that nothing the size of an ant, made of the materials that the ant is made of, could actually survive at that scale. It's like what happens is that basically as things grow, the amount of volume grows faster than the surface area of the thing, right? And faster than the strength of the materials that are there. And it's kind of a fascinating thing because it applies to shipbuilding, it applies to animals. Essentially you'll never have a mouse that looks like an elephant. It's kind of like just getting that big, things would kind of fall apart. You can use completely different building standards for creating cabins as opposed to skyscrapers. Once you're at that scale, lots of things have to go and change. And the way that he kind of termed this is kind of fascinating. He basically called this, it's called like the n squared law. And he sort of saw this as it's like a fight between surface area of something and the volume. And since the volume can grow much faster than the surface area, you have to basically sort of do something to basically give it more integrity as it grows. It seems kind of abstract, right? But I'll connect it in a few. So structure has to change as things scale. Have you ever heard of cliques at all? Cliques? It's kind of like you have a group of people who basically sort of like hang around each other and they're like best friends and they just kind of stay apart from some of the other groups. It happens in schools and sports teams all the time, right? So it's kind of like, hey, what do we do? It's like there's people in this particular team, they're not talking to anybody else, and it's breaking the fabric of our team or something like this. But it's important to recognize that you can model these things using graphs, right? You can say everybody who knows another person, they have a link to that other person. Or the links have the strength of the relationship that you happen to have there. And you can see in the graph when basically a subgroup starts to form. And it's kind of an interesting thing as it develops. So essentially what happens with this is like there's a tension in connecting to other people. Like if you basically know, like 10 or 15 people, it's kind of like in a group, it's kind of like hard to coordinate yourself, so there's a tension in doing that. So what happens is you start to break off into smaller groups. And this is like a very natural consequence of things. Have you ever tried to, say after a conference, go ahead and sort of arrange to have a group go to a restaurant, and you're standing outside the doors there, and you're going and saying, okay, well, let's go inside where we need to go. If you've got 10 people, it's almost impossible, right? Because everybody has constraints and different ideas about what's good food and what's bad food. And invariably, you have some people kind of making the decision, others kind of going along with it, right? Because there's tension there. It's kind of like there's a thing where basically for every piece of a network, every integral piece, it has a connection to every single one of the other people or entities. And all the others have one to everyone also. So it's an n squared growth law, right? And you'll see over and over again things as they kind of grow. This is a fight between n and n squared, okay? It's kind of like as things grow, you have lots of tension when they connect. So basically, they start becoming closer to n squared. You have to break things into pieces to actually sort of, have a functioning structure. And you go back for a second. It's like the thing with this. It's kind of that's the tension between n squared and n cubed. And in networks, we tend to see the tension between n and n squared. Are there other places where this exists? It's all over the place, right? Once you see this, you're going to see it all over the place. Have you ever heard of this at all, Miller's Law? It's basically something that was kind of found last century, where they basically figured out that people can't just remember an arbitrary amount of stuff quickly. What usually happens is you have you can hold 7 plus or minus 2 things in your short-term memory, and then you need to do something else to sort of remember more. And there's some people that have special strategies for memorizing pi out to 2,000 spaces and stuff like that. And it turns out that for us, we have the thing too that it's easier to remember these things beyond 7 or 8 or 9 or 15 if we kind of group them into chunks. And then you kind of think of the chunk and then you think about what's inside it. And that helps us basically form a grouping that basically allows us to decrease our cognitive load as we're working on things. And almost all of the data structures we have for collections are like this. Here's a binary tree, right? So basically at the top level, you don't need to basically know where everything is. You just need to have a sense of where it should be. And then what you do is you follow down that link, and you have a choice at every link until you get down to wherever you find the thing that you're looking for. Hash tables are the same thing. So this is basically about dealing with the tension of, new algorithms. It's kind of like, there's some algorithms where you have to visit every single element a couple of times, right? And there's others where basically you just have to visit almost once at most. And others where you don't have to visit every element. Okay, getting back to software. Okay, here's a set of class diagrams, right? This good design or bad design? Yeah, how can we tell from here, right? The interesting thing, though, is it seems like this one particular class member has a lot of data and a lot of functions in a way. And if you feel it's starting to get too big, the natural thing to do is start to look for some groupings. And when you see these groupings, you're like, oh, okay, this is a thing that kind of makes sense by itself. Maybe I can take this and put it someplace else. Maybe when I call something over here, it delegates to that. Your design becomes simpler as you take these responsibilities and break them out. And in many cases, we can just see them by the names, right? And that's really, I think, it's this thing of like seeing how things cohere together and just becoming, there's too much pressure, it's getting too big. I don't like it that way. Cell division, right, in biology, what's that about? The tension for growing a cell becomes too high that it has to divide into pieces. Okay, it's just like anything else biological. It can't grow too big without like dying, for instance, or you just need to go and sort of like have cell division. And that's just what happens in biology as an automatic process. The thing is, for us in software, it's kind of like that doesn't happen automatically. You can add functions to a module or a component, all day long and make it terribly, terribly complex. And there's nothing saying that this is a threshold past which you should stop, right? And basically create things elsewhere. So you can see that these notions of limits, they kind of like apply all the way around all the systems that we've got. And some of these limits are kind of cognitive. They're the way that we think and the way that we can think, the way our minds operate. And some of them are kind of physical in the sense that basically it's like a limitation in time or a limitation in space and all these different things. And the interesting thing is that they kind of intertwine, they interweave in a sense. Sometimes we'll think something is a physical limit and then discover, well, we really want pieces smaller than that, so let's go and make them because it'll help us understand things, right? So here's an example with this. Have you heard the idea of taking small steps when you basically write code, for instance? If you've never done test-driven development or something like this, the idea is basically don't try to do 15 things at once. Don't delay before checking in your code until 3 days from now, because the chances of you getting it right at that point are tough. Why is this a problem? Because of our cognitive limits. We can concentrate on a small set of things very quickly, get them done, feel confidence in it, and kind of like push them. So that's the thing. It's basically going and sort of like helping us sort of like make our jobs easier by going and sort of, you do this and then you kind of like, commit it, and then it's kind of something that you can move on to the next thing. You don't have to be overloaded with these things. Have you heard about this idea before? Limited work in progress? Okay, it was a big thing a while ago for like lean, software development. And the idea is basically don't try to work on 15 stories at once, no matter how big your team is. Instead, have like 1 or 2 stories that you're working on, and you basically complete those, and you're sure you complete those before you go on to the next one. And so why is this good or important? Well, it's good because it kind of goes and limits the ways that things can kind of fit together. Not limit the way things can fit together. But it's kind of like, it sort of like decreases the load on the team. And if you really bring everything to completion quickly, that's good. And if you basically have smaller things, like just one thing to bring to completion, you get the benefit of everybody on the team helping when they need to go and sort of solve the problem. So that's limited WIP. I want to talk about something which is kind of abstract here. So there's this interesting thing of mixing, right? So it's kind of like the thing with like the single responsibility principle that we talked about earlier. Like every abstraction should have a core basic responsibility and not do too many extra things. The reason that we like to do that is because when you share responsibilities inside of a class or a module and they start to mix with each other, it's hard to change one without changing the other. And if we get to do that, sometimes we introduce bugs because we get confused about this. So that's really like the problem of mixing. Is that kind of close to the issue with work in progress? In a way, it is. If you're basically working on too many things at once, it's kind of like you stop work on this and start work on that, and kind of like, everything becomes a bit of a jumble, and it becomes hard to concentrate and hard to keep things together. And you might have several things that you're working on which are unrelated, and people start to think they're related, but they're not, and it gets confusing. All right? So this is an interesting thing. Here we see that mixing is a problem in process, right? It's also a problem in structure, like for objects and classes and modules. So kind of funny that that kind of works out that way. So I kind of wonder, in a sense, it's like single responsibility principle. It might be that we sort of get at that generally by going and having small modules and small steps in what we do. And it's just a beneficial thing that we sort of like tell people to do all the time. You're running in trouble, take a smaller step, right? This thing is too hard to understand, break it down into smaller pieces. And those things tend to go and help us with this. And I think the interesting thing about it, though, is that when you basically are taking small steps, there's no chance to be doing several things at once, because you're just saying, I'm committed to doing this thing. And when you basically have small modules, it's kind of like, it's like you're on guard, that you don't want to have additional responsibilities in there. So when you do that, the responsibilities tend to come out in separate pieces, and that's single responsibility without even thinking about it. So I thought about all this stuff, and I was kind of thinking, it's like, what's really common here? And the thing that I think is common is the thing that there are certain pieces of advice that work both like for the structure of systems and also for the dynamic aspects of the systems, right? If you're working with iterations in software, it's kind of like it's better to have shorter iterations in order to go and sort of, get work done to completion early and sort of like have a good flow, right? And one of the things that can get in the way is if you're trying to do too many things at once. So if you become overloaded, we sort of pull out something, push it to the next iteration. And for, single responsibility in classes, it's the same thing. It's that essentially we sort of constrain things. We basically say, here's a limit. We want to basically keep things small. And we use the force of that constraining in order to go and actually sort of like choose to do something different, not mix responsibilities in that particular thing. So it applies no matter if you're talking about process or structure and systems. So I started thinking about this a little bit. I'm kind of thinking, okay, what is this really? And I tried to come up with a way of articulating it, and this is what I've got. The principle of deliberate context. And it's really basically this thing that essentially systems should be designed with intentionally bound contexts that are optimally sized for humans and for system maintainability. Each context should be large enough to encapsulate meaningful functionality, but small enough to be readily understood, modified, and reasoned about. So this is something that kind of applies to software in a way, right? We know the concept of bounded context from domain-driven development, but that applies to software also. Every module or class that you create is a context in itself. So you basically sort of pay attention to what is the cognitive load for understanding this thing, how many pieces in order to actually do, modify and things along those lines. And it's interesting to basically see in the time of AI that it's kind of like, it feels like we're reinventing modularity from first principles. You've heard of the context window in AI systems, right? It's like in an AI system, you can stuff lots of information in it, but it's kind of like you reach that thing of like, it's bigger than 7 plus or minus 2, but there's only so many things it can attend to at once. So people are reporting that essentially AI is helping them basically solve low-level quality problems, but then the quality problems tend to move towards the system level because it's all about the integration. And the AI is not able to basically, understand this whole system at once, in a way to be able to go and reason about it. So yeah, it is modularity in a way, but I think it's modularity with a couple of extras. And I think the thing with this also is like there's this entire thing of like, what's the risk and reward of making smaller pieces? And we'll get into that a bit later. But this is, you can argue that this is going too far, right, in terms of trying to find a general principle that, kind of like maps to a lot of the things that we do in software development. I mean, deliberate context, as I was mentioning earlier, it's like, in a way that applies to teams too, doesn't it? Okay, you basically intentionally put some people together to solve a problem. You don't want the team to be too big. You basically want to have them have a core purpose that they're basically trying to solve when they're doing things. And when you do those things, it tends to actually work out a lot better. So, there are other analogs to this. In French cooking, they have this notion of mise en place. And it's essentially this notion that essentially when you are cooking, what you should do is basically organize your workstation so you know where your knife is, you know where the butter is, you know where all the things are you're going to be working with. And that avoids the whole problem of running and trying to find, I need this special skillet to do my thing, right? If you do this, everything becomes much more ordered and reasonable. So this is, the thing with this. Here's a person who has a purpose, a single purpose. They're creating a meal. They define their context, and they have things in there they need to go and serve that particular context. And essentially, hopefully it's cohesive in the sense that that it's just one thing that you're kind of working on at a time. And it should be kind of clear where everything happens to be. And there's another thing too. I kind of was looking at like what are different pieces of context criteria. And I think this is what it's like. It's like if you are defining a context, you can always ask yourself, can it be smaller, right, without breaking anything? And if it can, try to make it smaller, right? Is it focused internally? Is it kind of like about a single thing, right? And so that's a thing to basically pay attention to. Is it clear? Can we understand this thing, when we approach it and need to go and do something with it? Is it small enough and simple enough for us to understand? There's a couple of other things too. Is it protected? And this is an interesting thing. I mentioned that thing about architecture, testing architecture. It's one of those things where basically architecture tends to kind of float and sort of get crazy after a period of time because nobody's paying attention, day to day about what's happening. But if you put fitness functions in place and things like this, you can actually start to get like very quick information when things start to deviate and do something about it. So what you're doing then is you're basically setting a set of invariants. These things should always be true in this architecture. Just like these things should always be true in my mise en place, right? It's just this thing of like we understand what's here, we protect this region. If you have teams, it's kind of nice to go and say, these are my teammates, these are the people I work with every single day, and I know who they are, and we can work together in a very good way. So if you try to reduce it down to something, to me it's like a little bit of a diagram. It's kind of like this. It's kind of like for anything that you're basically going and creating, or any way of working that you have, you basically want to go and make it coherent, focused on one thing. And you want to get rid of any of the excess that's there, and that's your right size for the thing. And it could be time or space or something. And you want to basically have it protected in many cases. Something which is really a boundary for you, right? And then beyond that, I didn't mention this one earlier, but it doesn't pollute. It doesn't put crazy things in the environment that go and sort of like cause trouble in the system it lives in. And it's very abstract, but imagine you're on a team, right? And essentially it's like you're creating trouble, you're putting bugs in the code. Is that a good idea? It might not hurt you in the team, but it's hurting other people around you. And it basically will actually affect the life of your team, if you can't fix it and somebody goes and says, hey, let's get another team together to do this, right? So you have to be careful about what you actually go ahead and produce and put in the environment. So yeah, I don't know how to reduce this into a smaller thing though, but it's funny with this, I think, because it's terribly abstract, isn't it? But I find that sometimes if I have a mental frame for things and I can ask some questions, then sometimes I can see things I wouldn't see otherwise. So this thing of kind of like, is it as simple as it can be, right? Does it have enough internal coherence to basically sort of function as it stands? And even outside of software, thinking about different things you can organize in life, it's kind of like this is what it means to be a good piece in the system, I think. And that's what we're all about in software development, right? We make the pieces and we put them together, And the principles that we use to do this kind of things are a side effect of forces in the system. Like, the entire thing which basically makes, an ant, impossible as the size of an elephant, right? It's the tension between, how many things one node needs to be aware of, and once it starts to go and grow and become something which is hard to manage communication, you need to go and break it into pieces and stuff like this. So anyway, that's what I want to talk about, and it's, that's NTAG overgeneralization, right? But I wanted to share it with you in the hopes that maybe you think about some of the concepts and you start to think about particular problems, particular process things, particular structural things, and ask yourself those questions in order to go and just sort of see if it fits. If it gives you an insight, that's great. And like I said, overgeneralization can be a bit of a problem sometimes, but it's kind of nice to basically have the capability to do this. So it's good to sort of like when you see two things that look like they're very similar, ask yourself whether they have something in common. And this is really what generalization is. It's like taking something and removing the inessential, and then that's the thing that you've got, right? It's a way of thinking, and this helps in everything we do in software development. So that's really what I wanted to go and share with you all. And hope you have a good rest of the week and everything, and hope you enjoyed the conference as well.